Hello everyone. Let us continue our discussion on binomial asset pricing model. In this binomial asset pricing model or CRR model, as also in the continuous time Black-Scholes-Merton model, you will encounter, or you have encountered, at least in this binomial case you have already seen that there are two probability methods with which you play around. One was the actual probability measure which we gave in terms of this. So, this is what we call actual or real world probability measure, and the other one which was helping us in expressing the price of the derivatives in a neat form is this probability measure p tilde, which we call it as risk neutral probability measure. Okay. And you also know the word, from where the word risk neutral came from and what does it mean. Okay. Now, in general, as I said, in this binomial asset pricing model as well as in the continuous time Black-Scholes-Merton model, you will encounter these two probability measures which you will play around. One is the actual, with which you try to use your statistical techniques to estimate the parameters to fit the model or whatever you want to do, if you want to specify the model specifically. And the other one is the usual construct that we have constructed in terms of p tilde q tilde, and we gave expressions for p tilde q tilde in terms of the binomial asset pricing model parameters, right. That was helpful in to us in expressing the results, which is basically the prices of various derivatives in this binomial asset pricing model. Okay. Now, the question will come like, what is the relationship between these two? Is there any relationship that these two? So, how do we move from one to the other, right, or is the question basically. So, this means we are asking what is the relationship between these two probability measures, right. That is what we are going to look at that now, and in this the idea is simple and you could see how exactly this follows, but in the continuous time model this will exactly be followed in a similar fashion. But there, as I said and repeatedly many times, things will not be that easy to understand really what is going on behind, but in case of discrete models, you can easily feel and you can easily understand step by step how exactly the results follows. Okay. Let us go ahead. So, in the general case, what we have in the scenario is we have a finite sample space, we have a finite Spanel space, and assume that there are two probability measures, right, p and p tilde, and both gives positive probability for each of these omega in the sample space. Okay. So, this is what then your assumption that, and if you look at this p and q, we assumed that p and q both are strictly between 0 and 1, and under the no arbitrage condition of the model, both p tilde q tilde was also between strictly greater than 0 and 1, okay, in the case of binomial model, but this is, you can say, in general for any finite sample space situation. Now, you will define a new quantity which we call it as z of w as the ratio. Okay. This is what, in this setup it is actually the ratio, right, but when you move to the continuous time model, this is really the derivative of one probability measure with respect to the other probability measure, and there is a name to this particular quantity z, and that is nothing but radon Nikodym derivative or simply we will call from now onwards as Rn derivative of p tilde with respect to p, sorry, with respect to p, right. So, this is what will be called as the Radon-Nikodym derivative, and this is one useful quantity through which you connect different probability measures and in general probability. That is what you will see in the even continuous type. So, here we have independently constructed p and p tilde, p is given, p tilde we have constructed, and we are trying to connect through z. In continuous time model we will use p, we will take p and use an z to get to p tilde. That is how we will define in continuous time. So, the understanding this would be helpful when we move on to that stage. Okay. So, this is really a ratio in the case of discrete time model, but it is actually the derivative in general. So, we call that as the Radon-Nikodym derivative or Rn derivative of p tilde with respect to p. Now, there are certain properties of this z which you can easily observe. A, probability of z greater than 0 is 1, and in fact this requires that z greater than 0 with probability 1, that is what this statement says. But in this particular case, since we have assumed for each omega both gives positive probabilities, so it is actually z greater than 0 almost surely, right, even for all omega, right, which is more than this, but this is sufficient. This you can observe easily from the definition itself. And B, which is expectation of z is 1, which is also from the definition. Z you have defined it as p tilde over p, and this expectation is, since we did not put e tilde, it is simply e. So, it means it is expectation under p. So, simple by definition. So, this follows immediately, right. To note, expectation of z is summation omega over omega, z of omega, p of omega. Now, substitute, you will end up with p tilde of omega, and this is 1. Okay. So, really you will see later that these two properties is what is going to be helpful in picking an z when we actually want to move from one to the other, or to pick an z such that it satisfies these two properties. So, these two are very important properties that you will recall even when you look at the continuous time model. In fact, the Radon-Nikodym derivative is the one that satisfies these two properties, is how, and you will take it up. Okay. Now, there is a small result which is also follows from the definition itself. You take any other random variable, for any random variable, say we call that as y, we will have e tilde of y is given by e z y. Remember, e tilde y means we are taking expectation of the random variable y under the probability measure p tilde, and e of z y means we are taking the expectation of the random variable z times y under the probability measure p. Now, this relates, right, the expectation of certain random variable under two different measures p and p tilde, and again you start with the right hand side, you apply the definition just like in the first line that we have. So, this is the proof for that part that we have. So, apply the same way, you will be able to notice that this is true, right. So, there is nothing much that you could do. Now, let us define. So, this is z is actually, it is suppose if you look at in the n period binomial context, right. So, this is, so far it is fine that for any finite probability space this is true, but if you look at actually in the binomial model setup. So, this z depends on all n periods in an n period binomial model. Now, we also would like to see the corresponding quantity which are dependent on or which are measurable with respect to fewer than n tosses or fewer than n period things, which, right. So, to do that, so we need the following definition which we call as Rn derivative process. Okay. right. So, what do we have? So, in an n period binomial model, let P and P tilde be the actual and risk neutral probability measures respectively, and also assume that both this gives a positive probability for each of those omega, then define the Rn derivative z at omega by the usual definition that you do, then the Rn derivative process which is defined by Zn equals expectation of Z given Fn for n 0 1 to n. You can see that in particular Z at n is the same as the Z that we have, because this is the n period binomial model, and Z at 0 would be 1, right, because expectation of Z is 1, that is what you will compare. Okay. So, this is what is the case that we call that as an Rn derivative process. You are given two probability measure and given you define the Rn derivative with respect to one measure with respect to the other, then the derivative process is given by this. Recall that this kind of things we have seen when we see martingale, that most of the martingales that we normally encounter are of this form. Now, you see that Rn derivative process is one such for such random variable Z, right, and this is what we have seen. And since as we just mentioned, you can easily observe that this is nothing but, so you can see this Zn, the process Zn is a P martingale. So, the Rn derivative process starting from 1 at time 0, it is a P martingale that gives you the Z at the end, which is what the Rn derivative process, Rn derivative is all about. Okay. Now, there is a lemma which is what is actually gives us the, we have already seen that how the simple expectations are connected between these two through Rn derivative. Now, through Rn derivative process, we want to connect the two probability measures in terms of the expectations. Okay. So, this is a lemma or result or whatever you want to call. So, this is basically the conditional expectation connection is what then we will see. So, we will assume the whatever we have written the conditions in the definition above. Okay. Okay. Now, if you have you will also fix two quantities, let m and n be fixed for the moment such that 0 less than or equal to n less than or equal to m and which is less than or equal to n. Okay. You will also take a random variable y, let y this be f m measurable. Okay. So, this is what you have. So, you have whatever condition that is written in the definition, and you are fixing two quantities m and n such that n is less than or equal to m in the binomial model, and we pick a random variable y which is measurable with respect to the higher index, which is capital M, sorry, small m in this case. Okay. Now, part A of this lemma is the simple connection which is much like the previous case, which you can easily see Z M Y. Okay. So, this is the simple relationship or simple expectation relationship with respect to the quantity S Z M and Y, which is F M measurable. Okay. This and then the next one, which is what really more general, of course, from which the first part is a special case. Y given f n is nothing but 1 over Z n E of Z m y given f n, right. So, this is as you see, like the second part is more generic in nature, and the first part, if you take f, since if you take n to be equal to 0, then you get really the first part. So, that is not really anything big, but this is the second part is what is most generic, which is what you need to understand and do. So, to the proof, the first part is very simple. Okay. Let us quickly see that this is actually expectation of. So, if y z is the R n derivative, then for any random variable we have already seen that this is what it is, right. E and E tilde are connected through z in this manner. Y is f m measurable and hence y is f capital N measurable, right. So, that means it is there in the full space. So, and hence this result is true, as we have seen this part is earlier itself. Now, this by the Tower property, right, you can write it as expectation of Z y given f m, right, which is then since y is f m measurable. So, you can write this as y expectation of Z given f m, right. So, you are using the y is f m measurable property that you are using, and then you are taking this out. First is Tower property, the second is the measurability property, or taking out what is known or iterated condition, taking out what is known property, and once you are. Now, what is this expectation of Z given f m as per our definition is simply Z m times y, right. So, this is the first part A, very simple. Okay. Now, for part B, first thing is what you want to show? You want to show that in the part B part E tilde of y given f m, right, f n, sorry, f n is nothing but is given the quantity given by the right hand side, right. So, you will use the characterization to show that something is a conditional expectation of some random variable given a sigma field under some probability measure. Then you have to show the two properties of characterization. One is measurable with respect to that sigma field, and the partial averaging property should satisfy. So, you use that argument here, and if you look at here, so what you would see, the right hand side is what you have to show that as E tilde of y given f n, and then the right hand side should be f n measurable, right. You see Z n is f n measurable. So, this 1 over Z n is in f n measurable, and E of Z m y given f n, right, whatever be this quantity, it is given f n. So, this part is f n measurable, and hence the RHS is essentially you can see is f n measurable. Okay. Now, this part we will utilize it, right. So, this is what we have seen that the RH is really the Fn measurable quantity, right. Now, this partial averaging property is what we have to check, right. So, to check PA property, right, partial averaging property is what then we have to check, right. So, you pick A in Fn and you consider the right hand side quantity, this is 1 over Zn E of Zm y given Fn multiplied by indicator function of A. So, you end up with this quantity, right, is what then you have to consider in order to look at that. Now, if I use the part A of this lemma for an Fn measurable random variable, right, this quantity is in an Fn measurable random variable. So, this quantity if I use this whole thing, if I consider as if the y in the part A with for Fn measurable random variable, because that is true for any m for an Fn measurable random variable, then it will be E tilde of that quantity would be equal to E of Z at that point, the Rn derivative process at that point multiplied by this y. Now, here Z n multiplied by, so the whole quantity will be multiplied by Z. So, this would then take the form as E of Zm y given Fn indicator function A. So, it is basically we are utilizing the part A of the result from part A of this lemma itself. Okay. Ideally, you can define it as a two different results and you can use it, but I thought it is does not matter too much. Okay. Now, this quantity, since my A indicator function A is in Fn. So, whether this is taking out what is known property, now we are bringing inside. So, this can be written as expectation of Z m y indicator function of A given Fn, right. This is what it is. Now, this, right, expectation of this, if I take the average of all those conditional expectation, what you will end up with expectation of Zm y indicator function of A, which again if I use the property, right. So, this will be equal to E tilde of y indicator function of A, again use of part A for Fm measurable random variable, right. So, right. So, what we have shown here is that the quantity that we have defined on the left hand side under the E tilde, right. So, without this IA, the quantity that we have here is nothing but the conditional expectation of y given Fn under the measure P tilde. So, that is what we have shown here. Now, what is the implication? Now, how this is helping us to do anything in the thing? The implication is basically on the risk neutral pricing formula is what we have said, right, in formula. So, what we did? We have a derivative, right. This is n period binomial model that we have in mind. Now, we know that V n is E tilde of V n given divided by n minus n given F n, right. Now, this is what. So, if I use the part B of the lemma for this conditional expectation of some random variable given F n under E tilde, if I transform this to E, then what you would get is 1 by Z n E of Z n, which is nothing but Z V n divided by 1 plus r to the power n minus n given f n for n 0 1 to n, right. So, you see here the risk neutral pricing formula, now you can express it in terms of the real world probability measure also, right. So, this would be same as this, that is what you have established, but now you need to know what is the Rn derivative process. If you know Rn derivative process, then you can use the risk neutral probability, instead of risk neutral probability measure, you can use really the actual or real world probability measure itself to compute the prices of the derivatives at times which is prior to maturity, right. So, there is more you can say that you can consider the process Zn over 1 plus r to the power n, and that is called a state price density process and so on, which if you are interested you can go through, right. So, this is what is the connection between that we have established between the two probability measures P and P tilde. Okay. Now, let us we will coming back to the last part of the binomial asset pricing model consideration, and the next what we will consider is something called as a Markov process. Okay. So, essentially this is to determine in the binomial asset pricing model or in general to determine what is relevant and what is not relevant, that is what is expressed in terms of the Markov process. So, let us define quickly the in binomial model what is the definition. So, what we have considering, we are restricting our attention to the binomial asset pricing model, but this definition is general, and n period binomial model is what then you are considering, in which you consider a process x naught, x 1 and so on x n be an adapted process. Of course, you need the adapted process. Now, what is the definition? If for every n which is between 0 and n, sorry n minus 1 you can take, n is really not required, and for every function say f of x or f, there exists or there is another function say which you call g of x or g, which might depend on n and f. So, for every f and for every n, right, there is another function g such that expectation of f x n plus 1 given f n is g of x n, then we say that this process x naught, x 1 and so on x n is a Markov process, right. So, you might have seen Markov process definition in some other ways, does not matter. So, this is also an equivalent way which you defining in terms of conditional expectations. What really it says is essentially the same, that if you had an idea about what is a Markov process. Look at this conditional expectation definition. Some function of the process at x n plus 1 given the information all the way up to n, right, which is what the best estimate is what this conditional expectation gives on the left hand side, is can be expressed through a function of the process value at time n, right. So, we are essentially saying the evolution from n to n plus 1 for the process to describe the process evolution from n to n plus 1 time period, all that information that is required from the past is the current state of the process, which is given by x n. So, f n is the complete information, x n is the value of the process at time n, right. So, this conditional expectation, if this is a function of g of x n, we have already seen such examples like expectation of, recall the example that we did, expectation of s 1 given s 2 which is a function of some such function, that g, right. So, what we need for every n and for every f, if there is g, if there is a g such that this is satisfies this, then the process is Markov, right. So, which essentially means that the conditional expectation is dependent on Fn only through the value of xn, right, that is what we say. Okay. Now, there is a result which we will use frequently even later to, which will help us, which gives us a tool to verify whether a given process is a Markov process or not. Okay. Since this we might require this even later, so we will state in generality, right. In the case of consider n period binomial model itself. So, we will let us consider a n period binomial asset pricing model, and let n be fixed such that between 0 and n. Now, suppose that there are k random variables that you are picking, which we call x1. This is not the square, but this is just the superscript which we are using, x1 to xk, or suppose that these are fn measurable, and you consider another some L number of random variables. Again, these are only superscript, this is not squares, y at L, which are independent of Fn. Okay. Now, let f be a function of all, some function of this k plus L random variables, right. So, this is f of x1, x2 and so on, xk, y1, y2 and so on, yl be a function of k plus L variables, okay, which are given by some function of some k plus L variables. Okay. And okay, so what are the variables? Which is essentially x1, x2, xk, y1, y2 and yl. So, these are the variables that you have, and you define a function g of x1, x2. Again, this is superscript, this is not power. Maybe we could have use a better notation, but does not matter, understanding is clear. Okay. Now, this is expectation of f with these values, and these arguments y1 to yl now are replaced by this random variables y1, y2 and yl. Okay. Then what you have? Expectation of f of x1, x2 and so on, xk, y1, y2, yl given fn is simply g of x1, x2 and xk. This is what this says. Okay. Let us try to understand what this tells. Okay. And so, you have some k random variables which are Fn measurable, some L random variables which are independent of Fn. Okay. Now, ultimately what you want to find? You want to find the conditional expectation of a function of these k plus L random variables. K of them are measurable with respect to the sigma field that you are considering, and L of them are independent of this Fn. Then what this says is this conditional expectation is simply given by a function g of these random variables x1 to xk, which are measurable with respect to Fn. And what is this function? This function is simply the expectation of some f of this, it became a function of this f that you have here, right. You keep this x1, x2, xk as at the dummy variable small x1, x2 and xk, right, xk, and replace this functions capital, keep this y1 and y2 as random variable and compute the expectation. Remember this is E, so it is we are talking about any general probability measure. So, in the binomial model case, of course, if you want whichever measure that you want to consider, that you will put accordingly. So, you compute the expectation of this function of this random variables. Remember, now this part expectation of this part, if I look at it. So, this part if I look at it, it is a function of these dummy variables x1 to xk and the random variables y1 to yl. So, you compute the expectation with respect to these L random variables by keeping this as fixed, then you get this function, which in the case of dummy variable x1 to xk, and replace the dummy variable by the corresponding random variable. So, that is what this expectation is, right. So, this is what it gives. Okay. So, now this we will try to use, we have already seen it in the case of earlier case itself. So, in the binomial model we will say that we will see that how this helps to identify that this process is a Markov process. Okay. So, what we have to show? So, this process is a Markov process. So, for every n and for every f there is a g such that expectation of f given s n plus 1 given f n is equal to some function g of s n, that is what we want to show. So, let us see how we can show. So, we consider expectation of some function of s n plus 1 given f n, but now you see that you are writing it as a some function s n plus 1, which is neither measurable with respect to f n nor independent of f n, right, that is clear. This is first n plus 1 coin toss, it depends this stock price at m n plus 1. So, it is not independent of f n, and also it is not f n measurable, right, this function of s n plus 1. So, we need to figure out a way how to do that. So, this trick is what generally you will use. So, you can write s n plus 1, okay. So, you can write my s n plus 1 as s n multiplied by s n plus 1 by s n, where what is this random variable? This takes value either u or d with probability p and with probability q, right. So, this is s n plus 1 by s n is just the result of the n plus 1th coin toss, which is either head or tail, which gives the stock price process either up or down with corresponding probabilities p and q, and s n is the quantity. So, now you can see that if I pick my this quantity as my x and this quantity as y, which is equal to this, right. Now, you can see that this one is essentially f x y given f n, right. So, of course, this is a function of x y. So, this is some function of some h of x comma y you can write, which is actually given as f of x y, right. So, this is a function of x y, right. Now, by independence lemma, because now we have expressed this quantity as in terms of two random variables x and y, one of them is measurable with respect to f n, the other is independent of f n, right. So, now I can apply the independence lemma to get what is the g of x function, which is expectation of f x y, right. So, this quantity, which if I remember, when y is independent of f1, expectation of fy given, fn would be simply expectation corresponding to the random variable itself, because it is independent of fn. So, that is what from where this comes. Now, what is this function? This is p f of x u plus q f of x d, right. This is the function now g. Then expectation of f of Sn plus 1 given Fn is simply g of x, which is Sn, right. So, but what we have shown? We have shown that Sn is Markov. We just took the definition we wanted to say and then use the independence lemma. So, whenever you encounter random variables which are neither measurable with respect to a particular sigma field or independent, then you try to find random variables some x1, x2, x3 and so on, some xk, some y1, y2, yl, such that some of them are measurable with respect to Fn and some of them are independent of Fn, and you try to express that particular random variable under consideration as a function of these k plus l random variable, then apply independence lemma to actually compute. So, essentially what we are doing is we are computing the expectation in this manner, right. So, that is what we are doing it here, right. So, this is Markov under this. Note, we did not we took E and PQ, which is if you are considering the binomial regressive model, this is actually the actual probability measure, but Sn is Markov irrespective of under both P and P tilde, okay. And this property, the what we call another note A, this is note B, the one step property can be extended, or it can imply, or it can be extended easily to multi-step property, that you can observe. So, because if you take one more step, right, with respect to n minus 2, suppose if you take and this, then of course you will have this. So, this is also true that the multi-step property also it will imply the one step property. Now, what is the implication, which is what is relevant for our discussion? We have this n period binomial model only in mind, okay. Now, in this case what we had? So, we had suppose if you take a random derivative V n, which is some function which I call it V sub capital N, this is a function, some function of S n, right. What are these derivatives? You can take simple European call, European put and so on, but this will not be say a path dependent option. If you take, then this is not true, but we are looking at the simpler case where this is a function of S n, right. So, what this says is that if you have a derivative which is a function of S n alone, means you are expressing say European call, European put, forward contract, all such derivatives will fall within this. So, any path independent derivative is what. Then my V n minus 1, right, would be E tilde of this quantity by 1 plus r given n minus 1, right, would now be if, so V n of S n, right. So, here S n is basically a Markov process. In general, even if you consider path dependent derivative, then you have to find the Markov, the corresponding Markov process and express the derivative in terms of the Markov process, a function of Markov process. But here we are taking simpler case, Sn is Markov, which we have already shown. So, we are taking this one. So, this is some function of the Markov process given some f n minus 1, the sigma field f n minus 1. Now, we know that for every n and for every function there is another function which is true, because Sn is Markov here. So, which means that there is another function v n minus 1 and this is a function of v n s at n minus 1, right. So, this is what you will see. So, this actually if you look at little bit more closely. So, this if I can write if I fixing the value, right. So, my this particular step, right, the right hand side equality, if I fix for some s, then I can even write what is my V n of S n. So, that is useful. So, let us write that part. So, this implies that my V n minus 1 at S for some is 1 by 1 plus R P tilde V n plus 1 in general. If I write this is n minus 1, n and n minus 1 we have. So, this is I am writing for any generic step plus q tilde of V. Okay, so I can write why to write. So, I will write only for this step alone. So, this is true that this is V n and this is V n of d times S, right. So, we know what is this function and so on, right. So, this is essentially it gives this relationship between V n minus 1 and V n, and this is also true for any one step that you look at it here. Okay. Now, in general you can also see that my V n would be right. In general, since you see the left hand side V n equal to E tilde of V n of S n 1 plus R to the power n minus 1 given F n is then would be by the multi-step property of this Markov process, right, multi-step Markov property, then this would be some function at time n, at time small n will be a some function of S at n, right. So, this is what will turn it. So, this is what is important step that you have. That means, if your derivative is expressed in terms of Markov process, then at any time prior to its maturity, if you look at its value or the price of the derivative, then that is some function of the Markov process at that point of time. That is what really you get here. So, this results, now we have the algorithm for computing the binomial the price of derivatives in the binomial asset pricing model. Now, we can look at the Markov based recursive algorithm, right. So, which is basically what you have a European derivative with payoff as this, or right, that is what you have, where my Sn is Markov. So, what will be the algorithm now? So, my V n at S is f of S, right, and my V at n small n at other times prior to this would be P tilde of V of n plus 1 U S plus Q tilde V at n plus 1 D times S for my n equal to n minus 1, n minus 2 all the way up to 1 comma 0. Okay. And accordingly, you can also write the delta hedging strategy in this particular case u of S n minus V at n plus 1 of d of S n by u minus d S n, right. So, the corresponding delta hedging strategy you have. So, what we have, this is the algorithm step that you have. So, this is what is the Markov based recursive algorithm. Now, if you want to computationally implement the binomial pacing algorithm efficiently, then one would always look for a Markov based version of the basic binomial pacing algorithm, and this is essentially that will give us. Okay. So, this is the implication of this Markov process. Once you identify that, then of course, you can simplify the computations, you can simplify the algorithm, and you can do an efficient implementation, because binomial asset pricing model is actually practically used with large number of periods. So, when you go for large number of periods, such an efficient algorithm implementation is what is required to be done if you have to really implement the theory in practice efficiently, right. Now, this with this idea of Markov based thing here, now let us consider the American options or American derivatives. Okay. So, you can make it American derivatives, which what is that? You know, we have already seen, you may be recalling what is an American derivative and European derivative means, right. So, in the case of European derivative, the difference is only on the exercise states, right. In the case of, suppose if you consider an n period binomial model, we will restrict our attention towards that. Then what you have is the European case derivative means it is exercised at only at the maturity time, which is capital N. But in the case of an American derivative, it can be exercised at any time, including the maturity, or any time prior to maturity also. So, which means there maturity time and exercise time are one and the same, but here maturity time is capital N and exercise times are 0, 1, 2 and so all the way up to capital N. That is what you have, right. So, that is what is the main difference, that the additional feature that you have is the early exercise option. Now, does it demand a premium, and which cases it is? Okay. So, simple case, since we have also considered only the cases with wherein the underlying stock does not pay a dividend. So, we will confine ourselves to that discussion on that, because binomial models are whatever we have considered, we did not consider the case of dividend paying stocks, it is only the non-dividend paying cases that we have considered. So, keeping that in mind, we have already seen in case of at least one derivative, that American call option, right. You have seen in the basic ideas, American call option is in a way equivalent to European call, because we have non-dividend paying stocks. Okay. So, European call, that means in this particular case, right, what you have is that the early exercise does not demand a premium, because it is always in case of this call, it is always optimal in a way, quote unquote optimal, to exercise at the maturity if it is the non-dividend paying stock. So, and hence you have this American call in some sense an equivalent to European call, but the same is not true with American put options, right. American put options, it is not true. Okay. So, we will now generally consider American derivative, which is path independent versions only, right. Path independent version one can do similarly, but we will not be handling that part. So, path independent case is what then you have, which means what? You have a derivative which pays off g at Sn at time n. This is, which means that the payoff is equal to g at time n if exercised at time n, that n could be any time between 0 and n, capital N in the binomial setup. So, what you have is this setup, right. So, you have a path independent option. So, let us take this s g of s n, some function where the g is actually the payoff function at any time n if exercised at time n, which means what? If you exercise at time n, then the payoff that you are going to get is g of s n, right. If you do not exercise, of course, then you have to hedge into the future, right. Now, earlier you recall that how did we determine the prices? If you go back to the arbitrage pricing theory argument itself, that you started at the last step, as last time point n, which is what is the payoff you determine at each state. Then you determine the amount required at the previous time point in order to hedge from that point to the next point, and you went this backward in time all the way up to 0. Now, what you have to incorporate? You have to incorporate the additional feature, which is that not just that you have to consider that the option is going to be not exercised at time n and it is going to be exercised later, which is what the European case is. Now, you also have to consider the additional feature that the option can be exercised at time n. So, the amount or the amount that you require at each time should be sufficient enough either to pay off if it is exercised at time n or to hedge if it is not exercised at time n. Okay. So, this suggests our previous algorithm that we have written, the Markov based one, to modify this as follows. Okay. So, the American algorithm American derivative pricing algorithm would then be equal to my V, I am taking with respect to this Markov g of s n. So, it is Markov based. So, at any time this will be the case, and so all these ideas that you are taking it here. So, this step would remain at this. Now, V at n at s would be, let us write that particular step which we written earlier, which is this part, right, p tilde of V n plus 1 s times u plus q tilde times V at n plus 1 s times d, right. So, this is what you had. So, earlier in the European case, this is what is the algorithm, right, algorithmic step. But now, as we explain that this particular quantity is required if it is not exercised at time n and if it is to be hedged for the future. So, the amount that is required, given that V n plus 1 is what given by this expression. But now you have the additional feature that this can be exercised at time n. Now, if exercised, then how much you need? You need g of s. So, this V n should be at least g of s, and in V n should be at least this much. So, that suggests that, right, this quantity be the maximum of these two for n minus 1 and all the way up to 0, right. So, this is then the American algorithm, where what you are looking at is that it is a maximum of, this is the exercise at time n part, and this part is if it is not exercised at time n, and at each time then what you need to have is this, at least either this or that, provided both options you have to consider, and accordingly you have to compute the price, and hence this is what it is. Okay. So, this is what is the American pricing algorithm in case of path independent option. Exactly the same even if you have any generic derivative instead of g of s n, if I take any f n measurable random variable as the payoff at time n, then I just have to replace this g x by appropriate that quantity random variable. That is what we will do that. Okay. So, now let us take the example. Let us take the example of an American put in a 2-period binomial model. 2 period binomial model, right. So, what you have your usual things that you assume R is equal to 1 by 4, U is equal to D 2 which is equal to 1 by D, and this gives my P tilde and Q tilde both as half. Okay. Now, American put, so the payoff, so my G at Sn, if I have to pay off at time Sn would be phi minus Sn, the positive part is what is the payoff that you will have here. Suppose, which means that it is an American put with strike phi, right. So, then if I simplify the or you can write down the algorithm step in a simplified manner and then do the computation, or otherwise you can directly do the computation with respect to each of this 2 period binomial model. So, 2 periods are the period, the binomial model would be, so you are starting, sorry I have not provided the S naught. So, S naught is my 4. So, S naught becomes either 8 or 2 and this becomes 16 and this becomes 4 or this becomes 1. So, in a 2 period this is the setup that you have, this is the underlying stock price process at various nodes and for various tosses. So, this is since it is a Markov based and we have incorporated American within that. So, this prices at time 2 you can easily compute at each of these nodes, this is going to be 0 and V 2 at 4 is going to be 1 and V 2 at 1 it is going to be 4, right. So, if I look at so the prices, so this is going to be 0 and this is going to be 1 and this is going to be 4 is the payoffs that you need at each of these nodes. Okay. Now, let us go back the previous step, V 1 at 8 will turn out to be maximum of, which is 8 here. Suppose if I look at here, it is 5 minus 8 the positive part which is 0 or the other part recursive part. Okay. So, this is maximum of, it will turn out to be 0 and if I compute the one step from these two values 0 and 1 and if I take the 1 by 1 plus r p tilde p q tilde both are equal to half. So, this is 4 by 5 times, or you can write say 2 by 5 times 0 plus 1 which is equal to now 0.40, and similarly V 1 at 2 will be max of now 5 minus 2 which is 3 and this part again will turn out to be 2 between 1 and 4. If I sum it up and then multiply by 2 by 5, then I will get this 2 which is 3. So, and okay, next step also we will compute and then we will see. So, V naught at 4 which is the time 0 price will be then maximum of 1 and the discounted value of 2 by 5 into 0.40 plus 3 would be equal to 1.36. So, if I really write down the prices at each nodes, so this is going to be 0.40 and this is going to be 3 and this is going to be 1.36, right. So, this is what will turn out to be the prices of the American put option in this particular case, right. So, now, so this is how you compute, and once you have this, of course, we are already given the delta formulation remain the same. So, there is not there is no difference between once you compute the VNs, then accordingly then you will compute the your delta hedging strategies in the usual manner, there is no difference here. Okay. Now, if I look at now here, if I compare with the, we said the corresponding the American call on a non-dividend paying stock is the price is the same as the corresponding European call option, but which is not the case with respect to the American put option. Now, if I compare this, so what would have been the price of the the corresponding European call option price, put option prices, if this is not an American, right? If I look at that, now let me put with a different color the corresponding values. So, that remains 0 here, 1 here, 4 here, because there is no difference in that. Now, between 0 and 1, since I do not have the I do not have the early exercise feature, then wherever I wrote this function maximum of something comma something, the second quantity, I need to worry only about the second quantity, because the first quantity, because it is not possible in the corresponding European case, right. So, the second quantity, and if I look at V18 and the maximum is attained through the second quantity, so that is going to remain as 0.40, there is no change. But whereas in the case of V1 at 2, the maximum is attained through the first quantity, which is the intrinsic value is what we call, which is the early exercise option gives 3, but if you do not exercise, you need 2, right. So, but in this case the corresponding European value is going to be 2, and now once this is changed, of course, this 1.36 is not going to be. So, in place of when you compute V naught of sigma, you will compute the second quantity, but now with 3 replaced by 2 if I compute, you will end up with 0.96, right. So, if I look at the time 0 price of this 2 period American put option, then the European put version is the price is going to be 0.96 and the American case it is going to be 1.36. And at the first time in the up node both prices are the same and the down node the prices are different and so on, you are observing, right. Now, these observations have some meaning, right. Now, this also tells you when to exercise an American call option or American put option in this particular case, when to exercise the American put option, right. So, if I look at the down node at time 1, what this tells is that the American value is 3, but the corresponding European value is 2, right. So, that means if I am the holder of this option, if I have the long position in the option, then it is optimal for me to exercise at time 1 if the stock price is down at time 1, right. If I do not do it, which means what? If I do it, I will get the value 3. If I do not do it, right, then I will lose that value, and at time 2 I will get either 1 or 4, okay, which on an expectation, the average value, even if whatever probability that according to that in this case you will do. So, it is will be less than, and what is the R here? It is 1/4. So, 1 period, but whereas if I take 3, if I had done this, I would have had a fixed quantity of 3.75, and if it is random payoff, then it is 1 and 4. So, right, is what then? It may be possible that I may get 4, but it may be possible that I will end up with 1, right. So, but whether if you compare these two, then obviously one would prefer 3.75 over the random payoff of 1 and 4. So, obviously this at time 1, then the down node you have an optimal exercise point, and that tells you wherever, I mean, if you look back the V1 at computation of V1 at 2 in the case of American put. So, this optimal is basically this is connecting to this part, right. This 3 is obtained through the first quantity. So, those are the time points in which it is optimal to exercise, because to continue hedge, okay, if you did not do, what will happen to the other party, the short position holder? What he will do? He knows if you did not do this, then he will need only he can consume 1, if you can compute and see, he can consume 1 and he can hedge the remaining 2, because that is what the corresponding European case is. He can hedge for the future. To reach 1 or 4, you only need 2 at time 1, to get to the value either 1 or 4 in time 2, right, and that is the hedging value that you have. So, he has the benefit in this particular case. If you let go an opportunity to exercise at an optimal time, then the short position holder will gain advantage. So, in this case the option holder, if option holder, if he fails to exercise at time 1, if when the stock price is down, then he lost an opportunity. So, this American pricing algorithm or American pricing problem is associated with also the question of when to exercise optimally, okay, which we will not explore in detail, but of course, this is a very complex theory behind when if you want to go further into that. But in simple binomial cases, I have already explained how one can detect whenever the maximum is obtained through the first quantity, you will always have an optimal exercise time points at those nodes, right, and which you can express also in terms of the other properties. Okay. So, this is with this we end our discussion on these American options. We have considered only the path independent payoffs in case of American American cases, which we have slightly modified the European case to account for the early exercise, and then we have priced it in fact American put you can any path dependent function, then this is similar way, and you can also identify what is the corresponding European and when it will be optimal to exercise the American option. So, with this we end the discussion on this binomial asset pricing model, which we have considered both the European case and American case, and we have considered the pricing problem in both these cases, and which prices main result was the risk neutral pricing formula, which gave us the prices, and the algorithm can be used to compute the prices if you want to implement this. Okay. So, we will take up this with this we end the discussion, and we will take up the other issues later. Thank you.